Hello friends, today we will discuss the various factors influencing the course of a nucleophilic substitution reaction, the mechanism, whether it is Sn1 or Sn2. Now you are given a particular the starting material and a nucleophile. Correct. Now how do we know whether the reaction is proceeding by the Sn1 mechanism or Sn2 mechanism? That is the topic for discussion today here. Correct. Now we can identify four different factors. The first one is the alkyl halide. Okay, the nature of alkyl halide, the identity of the alkyl halide. It is a very important factor here because we know that is CH3X, that is methyl halide. Then we have a primary alkyl halide or CH2X. Primary alkyl halide. Then we have a secondary alkyl halide. Then we have a tertiary alkyl halide here, R3CX. Okay, so the different types of alkyl halides are there. Now, identity of the alkyl halide is an important factor determining the mechanism of the reaction here. The second one, it is a nucleophile, whether it is a strong nucleophile or whether it is a weak nucleophile. Correct. Nucleophile, whether it is a strong one or weak one. Strong or weak. This is a question. Now the third one is the leaving group. Leaving group, we have seen good leaving group, bad leaving groups and all these things. That is better one leaving group or poor leaving group. Okay, different classifications are there like this here. Now, the most important thing here is the solvent. Okay, the solvent, whether it is a protic, polar protic solvent, polar aprotic solvent. Okay, I will be discussing this thing in detail later. That is protic or aprotic. So, all these factors will have tremendous influence on the mechanism of the nucleophilic substitution reactions here. Of this thing, the most important factor we can identify, it is the nature of the alkyl halide here. Now, we have seen the Sn1 mechanism here favors only a tertiary alkyl halide. That is, if you see, this is the methyl halide here, CH3X here. So, CH3X methyl and RCH2X, this is methyl and this is the primary one. All these two things give only Sn2 reactions. This gives only Sn2 mechanism here, Sn2 reactions here. Now R2CHX, this is the middleman. Okay, that is the secondary one. Then we have R3CX. So this is the tertiary one. The tertiary one, it gives only Sn1 reactions here. Now, as we go, that is the rate of the mechanism, reaction. Correct. Now, if you say the increasing alkyl substitution, we have seen increasing alkyl substitution. That means the hydrogen atoms in the alkyl halide is successively replaced by alkyl groups here. Correct. That is the identity of the alkyl halide. Okay, increasing alkyl substitution, it will favor Sn1 mechanism. Now, decreasing alkyl substitution, it favors Sn2 mechanism here. That means increasing alkyl substitution, this side. That is from here, if you go like this is the increasing alkyl substitution here. So, that is the rate of Sn1 reaction increases, increasing rate of Sn1 reaction. Sn1 reaction here. Now, decreasing alkyl substituents or substitution, it will favor Sn2 mechanism, like this. From here, we can see, so the rate of the, increasing rate of Sn2. Increasing rate of Sn2. That is alkyl substituents here. Okay, increasing alkyl substitution, it favors Sn1 reaction, and decreasing alkyl substitution favors Sn2 reaction here. Okay, Now, the next one will be nucleophile. This is the identity of the alkyl halide here. Correct. Now, the nucleophile, that is the next important point of the 4 different factors we have identified. The second one is the nucleophile. Nucleophile, whether it is a strong nucleophile or it is a weak nucleophile here. Okay. Now we have seen the rate of the Sn1 reaction, rate of the Sn2 mechanism. Two rate, the rate Sn1 we have seen, it is independent of the concentration of the nucleophile here. The rate here, it depends upon only the concentration of the alkyl halide. The nucleophile is nowhere in the picture. Therefore, the identity or concentration of the nucleophile does not affect the course of an Sn1 mechanism. Okay. Now, Sn2 mechanism. Now, the strength of the nucleophile is affecting. Here, we can say it doesn't affect the rate of a Sn1 mechanism. The identity or strength of the nucleophile. Okay. It is, it doesn't affect, do not affect the rate of an Sn1 mechanism, or an Sn1 mechanism is independent of the rate and strength of a nucleophile. Correct. So now rate of the Sn1 reaction, because it is the concentration depends only on the rate of the reaction depends only on the concentration of the alkyl halide here. Now, but in the case of an Sn2 mechanism, what happens? So rate will be, we know, that is depend upon the concentration of the alkyl halide and the concentration of the nucleophile here. Okay, the one is a unimolecular mechanism, other one is a bimolecular mechanism. We have seen those things here. That is Sn1, it is a unimolecular, that is a first order kinetics here. Okay, now Sn2 rate depends upon the concentrations of the alkyl halide and the nucleophile here. Okay, now the strong nucleophile in high concentrations, okay, it will favor an Sn2 mechanism. Correct? Sn2, that is a strong nucleophile and high concentrations. That is, strong nucleophile means the most common nucleophile used in Sn2 reaction, it will have a net negative charge, just like an OH minus group and all this kind of a thing. Okay, so now in the case of Sn1 mechanism, it is a weak nucleophile, because the nucleophile is not in the picture in the rate. It is not in the rate determining step or whatever it is. In the rate, deciding the rate, nucleophile is not in the picture there. Therefore, weak nucleophiles. So, weak nucleophiles such as say, we can say H2O, then we can say ROH. Okay, all these things will favor Sn1 mechanism here. Now the identity. Okay, here the strong nucleophile present in high concentrations, it favors an Sn2 reaction. Now the weak nucleophiles favor Sn1 reaction. Okay, now the most common nucleophile in Sn2 reactions, they bear a net negative charge. Correct? The most common nucleophile in Sn1 reactions, they are weak nucleophiles like water and ROH, alcohol here. Now, in the case of a secondary, that is 2 degree, here the problem comes here. Okay, the secondary alkyl halides here. Now here the identity of the nucleophile. Okay, it is important. The identity of the nucleophile is important not only in determining the mechanism of the reaction, and as well as for determining the stereochemistry. Correct. So nucleophilic substitution, we have seen that mechanism of the nucleophilic substitution as well as the stereochemistry. Okay, when a secondary alkyl halide is used as a starting material, then in this case the nucleophile is very, very important here. Now let us see an example. We will discuss with an example here. So consider a secondary alkyl halide reaction with a nucleophile here. Correct. So the secondary alkyl halides have the option. Is not very particular about an Sn1 mechanism or an Sn2 mechanism. Okay, there are two possibilities depending upon the nucleophile and depending upon the concentration of the nucleophile as well as the strength of the nucleophile here. Okay, secondary alkyl halides, they can react either by the Sn1 or Sn2 mechanism. So now, therefore, which one is the preferred mechanism? Okay, we are telling in the case of a secondary alkyl halide, both the mechanisms are possible here. So how do we know which mechanism is the preferred? It will depend upon the strength of the nucleophile here. Okay, depends upon the strength of the nucleophile. So if you say a reaction with, in the case of a secondary alkyl halide here, correct. So here, secondary alkyl halide is a strong nucleophile, OH minus. It can react with a strong nucleophile and a weak nucleophile like water. Let us examine which, so strong nucleophile always favor an Sn2 mechanism. We have seen that. Correct. Strong nucleophile present in high concentrations favor an Sn2 mechanism. Therefore, a secondary alkyl halide or CH2X here, it can react with an OH minus, that is a strong nucleophile, and it can react with a weak nucleophile. It will depend upon the strength of the nucleophile here. Correct. So let us see how the reaction is proceeding here. Okay. Now in the case of a compound of this nature, if we see, okay, now we can say two groups here, Br, then another group we can identify CA3. Okay, so this is reacting with the two types of nucleophiles here. Okay, it can react with water and it can react with so is a weak nucleophile H2O. Then it can have a strong nucleophile OH minus. Okay, now strong nucleophile favors, we know it is Sn2 reaction. Okay, so Sn2 reaction, what will be the thing from where the nucleophile will attack? So this compound is cis, because Ca3 group and Br bromine are on the same side of the ring here. So cis, say 1 bromo 4 methyl cyclohexane. So this is the compound we have just taken here, cis 1 bromo 4 methyl cyclohexane. So it can react with a strong nucleophile like OH minus here, sodium hydroxide or whatever it is. Then H2O, a weak nucleophile. Okay, now the strong nucleophile, it will favor Sn2 mechanism. Here it will be favoring Sn2 mechanism. And a weak nucleophile favors Sn1 mechanism here. Correct. So strong nucleophile attack, that is which is favoring an Sn2 mechanism. So the nucleophile attack is from the behind. Correct. From the backside attack. We have seen that backside attack of the nucleophile in the case of Sn2 mechanism here. Backside attack of the nucleophile. Therefore, what will happen? There will be inversion or configuration. That is Walden inversion we have seen in the case of Sn2 mechanism here. Now since here the bromine, that is the leaving group here, Br is the leaving group here, it is above the plane of the ring, the nucleophile, okay, it can attack from below the plane. And we will get only a one product here. So how it will be? Let us see. So cis compound, that is the nucleophilic attack of this, on this one, cis. This is bromine, this is the leaving group here, and we have a methyl group here. So, okay, that is cis 1 bromo 4 methyl cyclohexane, cis 1 bromo 4 methyl cyclohexane. So the reaction will be, say, suppose now when it is reacting with a strong nucleophile here, OH minus. Correct. So now this bromine, this is the leaving group. It will go with the electron pair here, and this lone pair here, it will come here. Okay. So it is a Sn2 mechanism here. Sn2, that is bone breaking, bone making, everything take place simultaneously. We know that it is a single step mechanism here. Sn2 mechanism. So we will be getting, that is an inversion of configuration. Inversion of configuration means this will be the nucleophile attacks from the below the plane of the ring here. Okay. There will be inversion of configuration. There plus Br minus. Okay, this will be a trans product here. Trans 4-methyl cyclohexanol. Trans 4-methyl cyclohexanol. This is the compound here. In the case of 4-methyl trans 4-methyl cyclohexanol. So that means the leaving group, the bromide, it is above the plane of the ring here. The nucleophile attack, it is attacking from the below the plane of the ring here. Okay, now we will be getting a single product. One product. So this A, this is giving a product B with an inverted configuration here. That is a Walden inversion here. This is the reaction with a strong nucleophile. Correct. Now weak nucleophile water, it will favor an Sn1 mechanism. We know that. Weak nucleophile favor Sn1 reaction. So Sn1 reaction occurs is a two-step mechanism. There will be an intermediate here. An intermediate carbocation which will be formed here. Loss of the leaving group. Okay, when the leaving group leaves here, a carbocation, it is formed here. Now we have seen that is the, now you know that carbocation, it will be undergoing the nucleophilic attack. And this carbocation, what is the geometry? It is a planar, trigonal planar carbocation. Therefore, the nucleophile, it can attack either from below or from above. No, there is no special preference for it. It can, attack from either side. Because carbocation, it has got a planar structure, sp2 hybridized carbon, it has got a planar structure. Therefore, the nucleophile, it can attack from either below or above. But in the case of an Sn2 mechanism, we have seen it's a backside attack. It will attack only from, the leaving group is above the plane of the ring here. Therefore, the nucleophile attack, it will be below the plane. Okay. Now, in the case of Sn1, we get a carbocation intermediate here. Now, and carbocation and intermediate planar structure, so the nucleophile can attack from either below or from above, etc., without any special preference. Okay. Therefore, we get two products here. That is racemization. Here it is inversion. We have seen it is Walden inversion of configuration. Now, in the case of an Sn1 mechanism, it will be racemization. That is two enantiomers in equal quantities. Okay. Therefore, now let us see and there will be finally there will be a proton transfer. That is instead of two steps, we can identify two steps Sn1 mechanism, and the final step will be the proton loss. Okay. So the proton loss, we will be getting the final neutral product here. So let us see how the reactions are now. Now, this is Sn2 we have written here. Now, let us see Sn1. So, this is our compound here. Br. Now, this will be forming an intermediate here. That is a carbocation intermediate. Okay, so this is the planar carbocation intermediate is formed in the case of an Sn1 mechanism here, two-step mechanism here. So this carbocation, it will be reacting with our nucleophile here, water. It's a neutral nucleophile here. So like this, the reaction will proceed here, plus Br minus. Okay. So now we can see there are two possibilities. The carbocation is a planar carbocation. Now the H2O, the nucleophile, it can attack either from below the plane of the ring or from above the plane of the ring. Now let us see above the plane how it will be. So here the water, that is a nucleophile, it is attacking from above the plane of the ring here. So what will be the nature of the product form? this methyl group is intact. Nothing happens to that. Here we get, the leaving group. It is a nucleophilic substitution. That is, leaving group leaves there and the nucleophile is getting substituted here. So we have oxygen, then water, OH2. Okay. There is a plus charge over here. Correct? So this is the product which we are getting from the nucleophile attacking from above there. Okay. Now what happens here? That is, now two steps are over now. New Sn1 mechanism. Now there will be a proton transfer here. Correct? This Br minus. That is, we have so this is the final step of the reaction, and we will be getting a neutral product here. Okay, so we will be getting, say, this is, both the things are above the plane of the ring here. Okay, this is the cis isomer. Cis isomer. Correct? And we will be getting HBr. So this is water attacking from above. Now, the next possibility here, it will be water attacking from below. The nucleophilic attack from below the plane of the ring. So what will be the nature of the products formed here? So this is CH3 methyl group here. So below means, see, like this only. Okay, then we have a plus charge here, OH2 here, like this here. So now this proton transfer reaction will take place here. Then that means a Br minus is here. So here this lone pair electrons here. Okay, so this will pick up this proton here. Correct? This is the reaction here. So finally we will be getting a neutral product here. So that will be a trans isomer. Okay, so this is the trans isomer plus HBr. Okay, so this is the trans one. So what is the relationship here? Two products are formed here. That is, first thing we have seen in the case of Sn2 mechanism, we have seen an inversion of configuration there. But here in the case of Sn1 mechanism, we are getting two products here. Okay, one cis isomer and another one is a trans isomer here. Two products are formed here. Okay, they are diastereomers of each other. Here they are diastereomers. The cis and trans isomers here, two products formed are diastereomers. Okay, that is the mechanism of the nucleophilic substitution reaction here. It determines the stereochemistry of the products formed here. Got the point? Now, the identity of the leaving group. Now we have seen the nucleophile here. So another important point here is the leaving group, how it is influencing the mechanism. So the leaving group, that is, the leaving group affects the Sn1 and Sn2 mechanism here. Well, a better leaving group. That means, it increases the rate of both the Sn1 and Sn2 reactions. See, there is no difference here. Both Sn1 and Sn2 mechanism, in both the cases, what happens? A better leaving group, if you are having, the rate of the reaction, it will be increased. Okay, a better leaving group, it increases the rate of both the Sn1 and Sn2 reactions here. Now, in the Sn2 mechanism, we have seen only one transition state is there. Sn2 mechanism, only it is a Sn2, it is a one-step mechanism. Therefore, there is only one transition state in Sn2 mechanism. Correct? It is a one-step mechanism. But in a Sn1 mechanism, we have seen there are two transition states here. Okay. So in Sn2, the slow step, it is the rate determining step. That slow step, it is the heterolytic cleavage, okay, of the CX bond there. Correct? Therefore, a slow, I mean a better leaving group. Okay, we are talking about better leaving group. It increases rate of both the reactions here. Correct? The better leaving group, the more willing it is to accept the electron pair in the CX bond here. Because we are concerned here with the CX bond here. The cleavage, heterolytic cleavage of the CX bond in both the reactions here. Okay, Sn1, CX bond, breaking of the CX bond and forming an intermediate carbocation is there. Correct? That is a two-step mechanism, and the carbocation is reacting with the nucleophile. That is Sn1. Now, in the case of Sn2, simultaneously bond breaking, bond making take place there. Okay, now the thing is X, the leaving group, the better leaving group. That means the rate of the reaction of Sn1 and Sn2, it will be increased. Okay, the better leaving group, it will be, means what? It will be more, willing to accept the electron pair in the CX bond, because when the CX bond is cleaved, cleavage of the CX bond takes place, the leaving group leaves with the electron pair in the bond. Okay, therefore, the willingness of the leaving group to accept the electron pair, okay, in the CX bond, means how, if it is willing, how far it is willing. Correct? So it will determine the ability of that leaving group, okay, to facilitate the reaction here. That is, the faster will be the reaction. That is, the more willing the leaving group it is to leave with the electron pair. That is a better leaving group. Okay, better leaving group means the more willing it is to accept the electron pair here. Therefore, electron pair in the CX bond there. Therefore, the faster will be the rate of the reaction. The rate of the reaction will be high there. Okay. Now, in the transition state, we have seen Sn2 mechanism. That is only, it's a one-step mechanism. There is only one transition state here. So, now in the transition state, what is happening there? That is the bond to the leaving group. It is partially broken. That is transition state. We have seen the energy diagrams there. So, in the transition state, so this is the situation. That is the partial breaking of the bond there. Okay, the bond to the leaving group, it is partially broken here. Now, increasing leaving group ability means that will increase the rate of the Sn1, Sn2 mechanism. Therefore, it will be CX, we can say R fluorine, the leaving group ability. Then we have, in the case of halogens here, okay. Then we have bromine. Then we have iodine. Okay. Therefore, in the transition state, the bond to the leaving group is partially broken there. Therefore, the increasing leaving group ability. Okay, how far it is willing to accept the electron pair and leave. It depends upon, it will determine the rate of the Sn1 and Sn2 reactions here. Now, in the case of the halides here, we have seen that is RF, that is the fluoride here. Then we have chloride, bromine, iodine here. This is the order. That is the increasing leaving group ability increases rate of the Sn1, Sn2 mechanism here. Okay. So, this is the third one, the leaving group ability. Now, the last one we will discuss, that is the solvent. The nature of the solvent, how it influences the Sn1, Sn2 mechanism here. That is solvent. You see, we have different types of solvents there. So the nucleophilic substitution reactions, they are, that depends upon the solvent. Okay. In the solvent play a very important role, rather, in the nucleophilic substitution reactions here. And so not only substitution reactions, even in the elimination reactions, which we will be discussing later, the solvents play a very important role here. So solvents, it will be acting as a medium of reaction. That is one point. Then, so it will stabilize the transition states and intermediates. Okay. Now, the solvents, we have different types of solvents, that is polar solvents. Then we have non-polar solvents. Correct. So, we have solvents are classified as polar and non-polar. So non-polar solvents means they are generally not used, because in the ionic or polar species in these nucleophilic substitution reactions here, they have limited solubility in non-polar solvents. Therefore, we are not using non-polar solvents. We use only polar solvents here. Okay. Now, the substitution reactions involve polar static materials. That is the reason there. Okay. Now, polar solvents are used to dissolve these static materials there. Now, in this polar solvents also, we have polar protic and polar non-protic. Polar protic solvents, polar aprotic, non-polar, polar non-protic, we use the word aprotic. Okay, that is protic solvents and aprotic solvents. Okay, now polar protic solvents, they are capable of intermolecular hydrogen bonding. The solvents, the polar solvents, they are divided into two categories. That is, one is the aprotic solvents and protic solvents. So protic solvent means what? It has got an active hydrogen atom, we can say. So active hydrogen atom means it is involved in the hydrogen bonding there. That is, or it has got a strong dipole interaction with other species there. Okay, so with compounds with active hydrogen, it contains functional groups like, say, we can say OH, then NH2, then COH, then we have SH. All these functional groups are there. Okay, the most common, polar protic solvents, we can say they are water and alcohol. These are the most common one. These are protic solvents, because the protic solvents, they can form hydrogen bonds there. Polar protic solvents, okay, they are capable of intermolecular hydrogen bond. Intermolecular hydrogen bonding. Okay, because they contain an OH bond or an NH2 bond. Correct? NH bond here. Because of that thing, with the alcohol, water, and all this kind of a thing. That is polar protic solvents there. Now, polar aprotic solvents are also there. So we will say, what is this polar protic solvents? Let us discuss the nucleophilic nature here. Polar protic solvents, how these solvents are influencing the reaction here. Let us see. Now, solvation, that is polar protic solvents. So, polar protic solvent, they solvate both cations and anions. How? Because there will be, in the polar protic solvents means, it contains the NH bond, OH bond, and all this kind of a thing, and they can form hydrogen bonding. We have seen that. Now, we can solvate both cations and anions. Okay, that is polar protic solvents. Okay, they solvate both cations and anions here. Cations are solvated how? By, there is a ion dipole interaction. Ion dipole interaction. What is meant by ion dipole interaction here? That is, suppose we have a salt here, say sodium bromide, NaBr. This NaBr, okay, it has got a cation, Na plus and Br minus anion here. So what we are telling, in a polar protic solvent, in a protic solvent, both these ions are getting solvated. Now the cations are solvated. Okay, now the the Br minus in the water is used as the solvent here, H2O. Water is used as a solvent. Means here the sodium plus Na plus cations, they are solvated by the ion dipole interactions with the water molecule. How it will be? Say we are having this ion dipole interaction means, see, this is our Na plus here. Okay, sodium ion, Na plus there. So it will be having interactions here. Interactions with water here. This is a water molecule, you can take it here. So there is a negative charge here. Oxygen, this is hydrogen, this is oxygen, okay, H2O. Therefore, it will have a partial negative charge here. So sodium ion is solvated by ion dipole interaction here. If from all directions you can see this kind of an interaction here. You see there will be an oxygen here, and this is the hydrogen, this is the hydrogen here. Okay, this is the negative charge, partial negative charge over here. So this side we can have that interaction here. This is called ion dipole interaction. That is, cations are getting solvated like this. And it is, solvation means it is putting the sodium ion, it will be, just like a cage formation here, we can say. Correct? So the delta minus here. Now, that means from all directions, you can say there will be this ion dipole interactions here. Like this, it will come. Sodium ion is solvated. We call it solvation of sodium ion here by ion dipole interaction with the water. Okay, interaction with the water here. So this is one kind of a interaction, that is the cation. Cation is getting solvated here. Now in the case of an anion, the bromide anion, Br minus, how it is getting solvated here? It is because of the hydrogen bonding here. Okay, so the hydrogen bonding will be, the bromide anion here. The center we have Br minus, and it is surrounded by water. In all possible directions we have this water here. It can form hydrogen bonding here. Delta plus, then we can have, say, like this. This is one thing. Then here we can have, this is the only water molecule I am just drawing here. Okay, there will be a delta plus here. Then we can have one here. In all directions, the hydrogen bonding we can show here now. Correct. Like this, we can show from all directions. There will be bromide ion. This Br minus, it is solvated by hydrogen bonding with water. This is hydrogen bonding with water. So these polar protic solvents, they are capable of solvating both anions and cations here. Okay, cations are solvated by ion dipole interaction, that is ion, Na plus sodium ion with the dipole interactions here. Correct? And in the case of anions are solvated by hydrogen bonding here. Okay, now sodium bromide, example we have seen, it is dissolved in water. Water is acting as the solvent here. Okay, so this is how in water it is happening like this here. Now polar protic solvents and nucleophilicity, how it is deciding the nucleophilicity. In the polar protic solvents, what is happening here? The nucleophilicity increases down a column of the periodic table here. Because this, as the size of the anion, say, size of the anion increases. Okay, it is opposite to basicity here. Okay, in the column of a periodic table, if you see, down the column of a periodic table, polar protic solvents, that is protic solvents and nucleophilicity. So in the polar protic solvent, nucleophilicity increases down a column of the periodic table as the size of the anion increases. That is, size increases means size increases, nucleophilicity increases. This is the order here. So in the case of basicity, it is the other way around. Okay, as the size of the anion increases, basicity decreases here. Now in the case of, say, let us see the example, halide series. Okay, now we can say fluoride, then we have chloride, bromide, then we have iodide. Okay, now down the column of the periodic table, okay, in this series, now the fluoride anion, it is a small electronegative anion compared to the iodide anion here. Okay, now iodide, it is the fluoride is well solvated by hydrogen bonding effectively, shielding it from the reaction there. Okay, a large and less electronegative anion like iodide anion, it does not hold on to the solvent molecules very tightly. Correct? Therefore, the solvent does not hide it is hiding the ion, we can say. The solvent does not, the solvent does not hide a large anion, nucleophile like iodide. And the nucleophile is much more able to donate its electron pair in the reaction here. Therefore, the nucleophilicity, okay, it will increase down a column of the periodic table, even though the basicity, decreases here. So the trend will be fluoride, is the increasing nucleophilicity. So this is how it is there. This is the trend here, increasing nucleophilicity here. So iodide anion, it is the, it is a very weak base here, but it is a very strong nucleophile. Okay, in a polar protic solvent. Important point, iodide anion in a polar protic solvent. So it is a weak base. Okay, weak base but strong nucleophile. So this is the influence of the solvent here on the nucleophilicity and basicity here. Iodide anion, it is a weak base, but it's a strong nucleophile in a polar protic solvent here. Now, what are the aprotic solvents here? So let us see aprotic solvents and its influence on the basicity and nucleophilicity here. Polar aprotic solvent. So we have, say, acetone, for example. It's a polar aprotic solvent. It cannot form hydrogen bonding. Okay, it doesn't have an NH bond or it doesn't have an OH bond here. Aprotic. Other one is a protic solvent. It forms hydrogen bonding here. Okay, now acetone. Now, if you have another compound, say CH3, C triple bond N. So acetonitrile. Okay, now this one. What is this compound? This is tetrahydrofuran, THF, tetrahydrofuran here. Now dimethyl sulfoxide. These are all aprotic solvents here. This is called DMSO, dimethyl sulfoxide. Okay, dimethyl sulfoxide. Then we can have dimethyl formamide. This is another polar aprotic solvent. Okay, this is dimethyl formamide, DMF. These are all polar aprotic solvents, acetone, acetonitrile, then THF, all these kind of things there. Okay, they are all polar aprotic solvents here. Now, polar aprotic solvents, they exhibit dipole-dipole interaction only. There is no hydrogen bonding there. Okay, there is no hydrogen bonding. Polar aprotic solvents, okay, they exhibit dipole-dipole interaction. They have no NH bond or they don't have any OH bond. Therefore, there is no hydrogen bonding. They are incapable of hydrogen bonding. Okay, now they solvate only cations well. Because the ion dipole interactions, polar aprotic solvents, they solvate only cations. They are, they solvate only cations by ion dipole interactions. Anions, now, anions are not well solvated because anions in the solvent cannot form hydrogen bonding. Just like in the case of, we have seen that NaBr case, we have seen that water, water, it is forming hydrogen bonding there. Here it cannot be done there. In the case of an aprotic solvent there, the hydrogen bonding possibility is not there. They can solvate only cations. Cations are. So anions are not solvated well here. Okay. So this will affect the nucleophile. Let us see the nucleophilicity now. Okay, when the salt NaBr is dissolved, say for example in acetone. Acetone, it is a polar aprotic solvent here. Okay, anions are not well solvated here because the solvent can, there is no hydrogen bonding here. NH bond, OH bonds are not here. Okay, now when the salt NaBr, okay, it is dissolved in acetone, for example. Let us see. Now the sodium cation, Na plus cations here. This Na plus cations, they are solvated by, the sodium ions are solvated by the ion dipole interaction with the acetone molecules there. So the acetone will be forming a cage kind of a thing surrounding the sodium Na plus there. Okay, so then now there is no possibility of hydrogen bonding. The bromide ions, they are not well solvated. Therefore, the bromide ions are surrounded by the solvent molecules, but they are not solvated there by the acetone molecule. So therefore, these are known as naked anions, because they are surrounded by these solvent molecules, but there is no solvation. So they are naked anions. This is known as, okay, the bromide anions are surrounded by the solvent, acetone or whatever it is. It is not well solvated by the solvent here, by acetone molecules there. Therefore, these anions are often called, okay, naked anions, because they are not bound by tight interactions with the solvent molecules there. Correct. Now, since the anions are not well solvated in the polar aprotic solvents here, there is no need to consider, to compare the nucleophilicity with the other anions here. Okay, so there is no solvation. Anions there are naked anions there. They are surrounded by the solvent molecules, but they are not well solvated there. So for the anions are not well solvated in polar aprotic solvents. Correct? There is no need, okay, to consider whether the solvent molecules are more, effectively hiding, say, one anion from the other one, and all this kind of a thing. So that kind of a comparison, it is not warranted here in this case here. Okay, now let us see another important point here. Now the nucleophilicity So the nucleophilicity and basicity follow the same trend in the polar aprotic solvents. Polar aprotic solvents, nucleophilicity and basicity follow the same trend as in contrast to the polar protic solvents. We have seen down the column of the periodic table, how this nucleophilicity increases and the basicity decreases and all this kind of a thing. But in the case of polar aprotic solvents here, nucleophilicity and the basicity, they follow the same trend here. The stronger the base, stronger the nucleophile. That is as simple as that here. Okay, now the basicity decreases with size down a column of the periodic table. In the same way, nucleophilicity also will be decreasing. Say, here we have seen the fluorine, then chlorine, bromine, iodine, and all this kind of a thing here. So this is the trend here in this way. So increasing nucleophilicity in polar aprotic solvents here. So increasing nucleophilicity. Okay, in aprotic solvents. Correct? So this is the trend actually. Nucleophilicity and basicity in polar aprotic solvents, there is no difference here. Okay, now another important point here which we have to consider. Now, in the case of polar protic solvents, where the nucleophilicity we have seen now, Sn1 and Sn2 mechanism, how it is, the solvent is affecting the Sn1 and Sn2 mechanism here. Now, polar protic solvents, they are good for Sn1 reactions here. Okay, Sn1 reactions. Polar protic solvents. Polar protic solvents are good for Sn1 reactions here. Now, aprotic solvents for Sn2 reactions here. Polar aprotic solvents are good for Sn2 reactions here. Now, polar protic solvents, we have seen that, like say, polar protic solvents, we have seen example H2O, ROH, and all this kind of a thing we have seen. It can form hydrogen bonding here. Okay, it can solvate both cations and anions well. Correct. So this characteristic is important for the Sn1 mechanism here, because we are getting a there will be a carbocation intermediate is formed. Correct. Sn1 mechanism, two ions are there, a carbocation intermediate and a leaving group. Okay, the stability of the carbocation intermediate. Okay, so in the case of Sn1 mechanism, what is happening there? Polar protic solvents. Polar protic solvents, because polar protic solvents are capable of solvating both the cations and anions there. Okay, now this is very, very important in the case of an Sn1 mechanism, because Sn1 mechanism, it is a two-step mechanism. The first thing is the halide, alkyl halide, there is a heterolytic cleavage of the CX bond there, and we are getting a carbocation intermediate, positively charged one, and a leaving group Br minus. Therefore, we have got two ions, one a positively charged cation and a negatively charged anion. Now, both this carbocation and the leaving group ions formed by the heterolytic cleavage of the CX bond here. Okay, now both these ions are solvated here. Correct? So, both these ions are solvated by the polar protic solvents here. Okay, that is, both the ions are solvated. Okay? Both cations and anions are solvated by the polar protic solvents here. By ion dipole interactions, we have seen that with the polar protic solvent, that is, the carbocation, it is getting solvated by the ion dipole interaction with the protic solvents here. Okay, now the leaving group is solvated by hydrogen bonding, that we have seen. Okay, now these interactions, it will be stabilizing the reactive intermediate here. Correct? Now the polar protic solvent is generally needed for Sn1 reactions there, because the stability of the carbocation is important, very important point there. Okay, therefore, in these Sn1 reactions, we are using only polar protic solvents there. Okay, now aprotic solvents, polar aprotic solvents, okay, they exhibit dipole-dipole interactions only, but not hydrogen bonding. We have seen that now. So as a result, they do not solvate the anions formed. Correct. Therefore, this has got a pronounced effect on the nucleophilicity of the anionic nucleophiles there. Okay, now these nucleophiles, they are not hidden by the strong interactions. Correct, with the solvent. They are more nucleophilic. Okay, now strong, because the stronger now we have seen that strong nucleophiles, it will favor Sn2 mechanism. Therefore, polar aprotic solvents are especially good for Sn2 mechanism there. Correct. This is how we have to interpret here. That is, aprotic solvents, aprotic solvents, we have only dipole interactions there, but not hydrogen bonding is there. Correct. As a result, they do not solvate anions well. This has a, it has got, so the nucleophilicity is getting affected there. Okay, the anion, the nucleophilicity is getting affected. These nucleophiles, they are not hidden by the strong interactions. Correct? Nucleophiles are not hidden, surrounded by the solvents and hidden there. Correct? So, they are more nucleophilic, therefore. That means, in Sn2 mechanism, we want stronger nucleophiles. Stronger nucleophiles favor Sn2 mechanisms are there. Correct? Therefore, polar aprotic solvents, they are especially good for Sn2 reactions. Correct? Now, in the case of, say, for example, now let us see the interesting aspect of it before I conclude. Now, in the case of a secondary one, alkyl halide, say we have, say, R2CHX, a secondary alkyl halide here. So it can proceed, here the reaction can proceed Sn1 or Sn2. This is the interesting point here. Okay, which mechanism it will take here? Mechanism depends upon the conditions there. Again, okay, now if you are having a strong nucleophile, it will favor Sn2 mechanism we have seen. Okay, over the Sn1 mechanism. Okay, we have the two choice here. A secondary alkyl halide, it can undergo Sn1 reactions or Sn2 reactions here. So, what are the conditions? If you use a strong nucleophile, we know it will favor Sn2 mechanism. So, for example, now if we have, say, RO, OR. Okay, OR minus, it is a strong nucleophile compared to ROH. ROH is a weak nucleophile here. Okay, therefore, RO minus, this will favor, Sn2 mechanism, whereas ROH, it will favor Sn1 mechanism. Okay, weak nucleophile here. Correct? Therefore, so polar protic solvents and aprotic solvents, these are the two things here. Now we have seen polar protic solvents. Polar protic solvents, they favor Sn1 reactions there. Okay, because of the the ionic intermediate. Protic solvents, ionic intermediate are stabilized by solvation here. Okay, and in the case of polar aprotic solvents, the Sn2 reactions are favored because the nucleophiles, they are not so well, nucleophile anions are not well solvated, and therefore they are more nucleophiles here. Now let us see the so this one, say water, ROH, and all this kind of a thing, alcohol and all. This will all favor Sn1 mechanism. We have seen that now. Acetone, DMSO, dimethyl sulfoxide and all this kind of a thing, they are polar aprotic solvents there. Correct? Therefore, they favor Sn2 mechanism there. So DMSO and all this kind of a thing favor Sn2 mechanism here. Correct? Therefore, that is why it is depending upon the condition here. Now, let us see one problem here. Now, how will you summarize this thing? So, suppose we have this alkyl halide CH3X here. So, CH3X, it is, and R CH2X. Correct? This is a primary one. So, here the mechanism favored is Sn2. Okay? So, it is favored by strong nucleophiles, polar aprotic solvents. Okay? Now, it will be, the nucleophile, strong nucleophile with a net negative charge over that. Correct? Now, this is the thing here. Now, if you are having R3CX, this is a tertiary one. So, the tertiary one, it usually favors the Sn1 mechanism here. It is favored by weak nucleophiles we have seen, usually a neutral one, and polar protic solvents. One is aprotic solvent and protic solvent here. Now, if you are having a this thing here, say CH3, CH2, say Br, leaving group Br here. So, this is reacting with the acetylide anion. This one. So, what will happen here? What is the type of reaction? The mechanism in a nucleophilic substitution reaction here, acetylide alkyl halide is a primary one. It is a primary alkyl halide. So, what will be the type of reaction here? So, primary alkyl halide, it proceeds with by Sn2 mechanism here. Okay, this is what you have to understand. This is Sn2 mechanism only, primary alkyl halide. So, the nature of alkyl halide is important in determining the mechanism of the reaction here. Correct? So, the primary alkyl halide, it in a Sn2 mechanism here. So, we can say the product formed will be simple. Correct? Like this it will come. Now, tertiary alkyl halide, that will react by the Sn1 mechanism. We have seen that thing, So, Sn1 reactions, it will proceed with racemization. Correct? So, just one small example I can just show here. Say a compound of this nature. So, we have a methyl group there, then a chlorine, then another methyl group here. Okay, these are a methyl group here. So, it is reacting with a CH3OH alcohol here. So, this is a tertiary one, alkyl halide here. Okay, it will react by Sn1 mechanism. We know that. And methyl alcohol, it is a weak nucleophile also. So, Sn1 reaction, it proceeds with racemization at a single stereogenic center here. So, two products will be formed here. this one, correct? So this will react with the methyl alcohol here, methanol. So Sn1, we get two different types of products here. Racemization will be there. So here you can attack here, correct? Then another possibility will be other that is above the plane, correct? One will be below the plane, other will be I will just draw here. Other compound formed will be okay. It will be above the plane. Below the plane here. Correct. Like this. You know the alkyl halide, influence of the alkyl halide and all these things. Okay, so thank you very much for listening.